Find the eigenvalues and eigenvectors of A. So first we find the characteristic equation, which is determinant of A minus lambda I equals 0, or determinant of lambda I minus A equals 0. So let me use this, same thing though. So lambda I minus A first, then I'll take determinant in a moment. So here lambda I minus A, lambda is just unknown number, eigenvalue, that's what we are trying to find. I is an identity matrix, in this case 3 by 3 identity matrix. So I, in fact I3 in our case, which is 1 0 0 0 1 0 0 0 1, and when we multiply by lambda, we multiply each component. So that lambda I is in fact lambda 0 0 0 lambda 0, okay, minus A. A is the given matrix, 1 0 3 negative 3 4 1 0 0 2. Now we subtract this. So we subtract component wise. Lambda minus 1 is here, negative 3 3, lambda minus 4, negative 1 0 0, lambda minus 2. So we have this matrix. Now we want to take the determinant, okay. Then determinant of this lambda I minus A is equal to, now let's expand along 0 0 by lambda minus 2, or we could expand along this. So I'm going to expand along third row, okay, expand along third row. So positive, negative, positive, and 0 positive, negative, positive. So we don't have to do anything here. Positive, negative, positive, negative, positive. So here comes lambda minus 2, that leaves a 2 by 2 determinant. Okay, so lambda minus 2 row column, we just delete that. We got lambda minus 1 0 3 lambda minus 4, and we know how to find this. We just multiply this way, minus 0. So this is pretty much lambda minus 2 outside. When we multiply these two, we get lambda minus 1 lambda minus 4 minus 0, we don't need. So this is the determinant of lambda I minus A. We set this equals 0, okay, setting lambda minus 2 lambda minus 1 lambda minus 4 equals 0, we get the eigenvalues, and they are lambda minus 2 is 0 when lambda equals 2 1 and 4. So we got 3 distinct eigenvalues. Now we need to find corresponding eigenvectors for each of these eigenvalues. Okay, that's a lot of work. Let's do it. Let's take lambda equals 1. So for lambda equals 1, I mean, you can take for lambda equals 2. So what we do is, this is like AX equals lambda X, and we are trying to figure out this X, by the way. And this is same as if we move over, so lambda minus lambda I in terms of matrix minus A X equals 0. So we're gonna solve in this way. It's pretty much like lambda I minus A. Instead of determinant, now we have matrix. Okay, that's the matrix, and we don't take the determinant, and we get this vector X, that's the eigenvector. Okay, so lambda I minus A is in fact here. If I come back here, this is lambda I minus A. Okay, this is what we're gonna use. So let me delete this here. We're gonna use this over and over for different lambda values. This is lambda I minus A. Now for lambda equals 1, we're going to work on this. Then for lambda equals 2 and for lambda equals 4. Okay, so for lambda equals 1, we're gonna get, what is lambda equals 1? So I'm gonna write lambda I minus a x, that's to be determined eigenvector, is equal to 0 implies, we can just write down the corresponding augmented matrix. Okay, this is pretty much finding the null space of this matrix. So lambda equals 1, let's plug in here. So 1 minus 1, 0, 0, negative 3, 3, 1 minus 4 is negative 3, negative 1, 0, 0, 1 minus 2 is negative 1. I am just writing the augmented matrix. This x has 3 components, x1, x2, x3, we don't need, and let me put 0 there. Now we do row reduction and determine the variables for x. So we can always think x, x1, x2, x3, 3 components, the first being x1, x2, x3. Okay, so let's do some row reduction. Obviously we want to put 1 or this, so swap, interchange row 1 and row 2, we get 3, negative 3, negative 1, 0, and the second is 0, 0, negative 3, and last is 0, 0, negative 1, 0. Okay, just interchanging row 1 and row 2. So here is a pivot, there is no pivot. Oh, here using this, or we could have written this one on the top, same thing. Let's make this 0, because negative 1 is pretty much, if we multiply this by 1/3, negative 1/3, then this becomes 1, and 1 in negative 1 would be 0. So when we have only 2 numbers, I mean 0, 0, I mean they are linearly dependent, so this row has no effect. So this one, 3, negative 1, 0, 0, 0. So we can divide by negative 1, in fact divide by negative 3, so that this becomes 1. So if I multiply each by negative 1/3, which is same as dividing by negative 3, I'm gonna get 0, 0, 1, 0, and when we have 1 here, then we add, we get 0, 0, 0, 0. And this is for x1, this is for x2, this is for x3. Here is pivot, no pivot, here is pivot, so x2 is free. So let's solve this. So x2 is free, and from this one we get x3 is 0, and from the first row we get 3x1 minus 3x2 minus x3 equals 0, but x3 is 0, so no, this is gone, just gone, and x2 is free, so 3x1 is, move this over, 3x2. Now we divide by 3, we get x1 is x2, and x2 is any real number. So we have x, so thus x is, in fact, we are just writing a basis for the eigenspace or eigenvector. So x1 is x2, x2 is just x2 because it's free, and x3 is 0. We can factor x2 out, then that gives us 1, 1, 0. So this is a basis or eigenvector, basis for the eigenspace or eigenvector related to 1, and sometimes we call that eigenpair. Let me put that. Eigenpair is for 1 eigenvalue. For this eigenvalue we got 1, 1, 0, 1, 1, 0. Now we need to repeat this for 2 more eigenvalues. We are done for the first eigenvalue, lambda equals 1. Now let's do for lambda equals 2 and lambda equals 4. So for lambda equals 2, go back to this lambda I minus a matrix and plug in lambda equals 2. So when we plug in, the augmented matrix is this. Using this 1, we can make this 0. Just do the row reduction. Okay, follow this and you get this. Now we got pivot here. Here is a pivot. There is no pivot, means x3 is free. The vector x is, we can think x1, x2, x3, and x3 is free. So from this one, negative 2x2 plus 8x3 is 0. Then we get x2 equals 4x3, where x3 is free. Similarly, from the first row, we get this. Thus, the vector x is x1, that's 3x3, x1, x2, x3, and we can factor x3 out. That gives 3, 4, 1. So this is a basis for the eigenspace or corresponding eigenvectors. So there are infinitely many correct answers, so one of them is 3, 4, 1. So we can put them as eigenpair. So 2, 3, 4, 1. Eigenvector, eigenvalue, eigenvector. Now for lambda equals 4, again the same thing. Plug in 4 here, and lambda I minus a x equals 0, and we get this. Now we can make this 0 using this row reduction. Then we can multiply first row by 1/3, and this negative 2 to 0, everything 0, and multiply this by negative 1/2. We get this. Pivot here, there is no pivot, so x2 is free. So from this one, 1 x3 is 0, x1 minus x3 is 0, and x3 is 0, so x1 is also 0. So in this case, x is x1, x2, x3. We can pull x2 out. We get 0, 1, 0. So this is a basis for the eigenspace or eigenvector, corresponding eigenvector 0, 1, 0. In fact, there are infinitely many correct answers. And we know that these eigenvectors 1, 1, 0, 3, 4, 1, and 0, 1, 0 are coming from distinct eigenvalues, so they are linearly independent. Okay, final.